Okay, so this marks the last video series in our course, where today we'll be talking about second-order circuits. These are circuits that are characterized by a second-order differential equation. So in other words, we've got resistors and reactive elements, but we have the equivalent of two reactive elements, so an L and a C, for example, in our circuit, such that we get the second-order differential equation out of it. And just as a reminder, in Chapter 7, we talked about first-order circuits. We had either a resistor or capacitor equivalent or a resistor inductor equivalent. So the storage elements, i.e. the reactive elements, act to increase the order of our differential equation describing our system. So we have two primary examples of this, as I'll show on this page, and the first is called the series RLC circuit. So we've got the resistor, inductor, and capacitor component all in series with one another. And we have the parallel RLC circuit. Both of these are second-order circuits and are described by two different differential equations. Of course, it makes sense to drive the series circuit with a voltage source and to drive the parallel circuit with a current source. So these circuits behave similarly to those that we've seen in Chapter 7, which were the first-order circuits. In other words, we have a source-free decay natural response of the circuit, as well as we can have a forced function response of the circuit. So let's examine that for these examples. Okay, first let's examine the natural response of a series RLC circuit. So here's the series RLC circuit. Natural response means that the inductor and the capacitor are initially charged. There is no independent voltage or current source in the problem, and we're going to examine the decay response of this system. So we need to quantify the initial voltage across the capacitor, Vc at time 0, and that's going to be given as V naught, and the initial current through the inductor, IL, which is going to be IL times 0 equals I naught. Okay, so a couple little equations we can write down right away. The initial current at time 0 of this system, and we can abstract that to just being the current through all elements I at time 0, is just equal to the initial inductor current. And the voltage across the capacitor is related to that current as 1 over the capacitance times the integral. See, at time 0 it would be evaluated from negative infinity to 0 of I, and that integral evaluates to voltage V naught as given in the problem. And since this is just a single loop circuit, we know from our past experience that all we need is a single KVL expression in order to solve this problem. So first we're gonna follow the way I've drawn the current. So I'm gonna walk around clockwise and first describe the voltage across the resistor, VR, and that's going to be given by the current times the resistance. So it's just IR is the voltage across the resistor. The voltage across the inductor, that's VL, which equals L di dt. So that's L times the first derivative of that current I. And then the voltage across the capacitor, which is 1 over C times the integral time t of I must equal 0. Okay, so we can get rid of the integral by taking the first derivative of each term. So taking the first derivative of each term with respect to time, we get d dt of I times R. And remember, these i's are functions of time, so I'll be explicit in this statement. Times L times the second derivative of I with respect to time plus 1 over C times I must equal 0. Okay, so now let's divide each term by L in order to rewrite this differential equation with the di squared term first without a coefficient. So doing so, again, dividing each term by the quantity L, I get di dt squared plus r over L di dt plus 1 over Lc times I. And this is the second order differential equation that represents the series RLC circuit. A couple things to note here. We again see the R over L and the 1 over LC terms are appearing. Okay, in this system, these are going to be important quantities. Remember, the R over L is the inverse of the time constant for an RL circuit. L times C is an interesting quantity, which we'll understand a little bit further in a moment. So one thing I want to note before we move on is, just like in Chapter 7 when we had a first-order differential equation, for that we had to find the initial conditions of the inductor current and the capacitor voltage in order to solve. With a second-order system, we also have to find the initial condition of the current through the inductor and the voltage through the capacitor, but we have a second term that we need to find initial conditions for, and final conditions, I should say, and that is the di dt term, or the first derivative term. So instead of just finding the initial voltages and the final voltages and currents, we need to find the initial and final conditions of the first derivative.